Okay, welcome back everybody. So this is section 5 of chapter 12 on climates and climate change. And now we're going to be getting into the concept of global warming. This is going to be what section 5 is about. So global warming is really, you might call it an instrumental record from the past 60 or so years of literally recording with human instruments the warming of temperatures around the Earth. We're pretty sure it's a result of burning fossil fuels, that is things like gasoline, or oil, petroleum, coal, natural gas, and gasoline is a derivative of one of those. And a result of burning fuel is that, I should make that a different color. One of the byproducts of that is carbon dioxide. Carbon dioxide. And so we know carbon dioxide to be a greenhouse gas. Burning fossil fuels, we're pretty sure, has been resulting in warming up the atmosphere. Now this happens naturally. Volcanoes kick out CO2, of course, but human processes really have accelerated that in recent years. Okay, so we get energy from the sun, as you probably know. And you might say that we have an energy budget. That means, like, if you make a budget, like a financial budget, you have a certain amount of money that comes in and a certain money that you're paying out for various things like bills and gas for your car, etc. All right, well, the same thing is true of the energy from the sun. All right, we receive energy from the sun, energy in, but the Earth reflects some energy and also retain some too. So you can think of that as being money that you save, or energy that is saved. Well, the problem is, however, we don't want to save too much energy. That is, we don't want too much energy on our Earth because that's what drives up the temperatures of the Earth. And so, unfortunately, we've got more energy coming in than is lost to space. And so that energy from the sun coming into the Earth is being either absorbed or retained more so than it is lost. So I guess if that were a financial budget, that would be a good thing because you'd have more money. With an energy budget, it's a bad thing because we have too much energy in our atmosphere driving up temperatures. So what those last two lines of that previous slide talk about is the fact that energy from the sun, that is like shortwave radiation from the sun, all different kinds of radiation really, but comparatively short wave radiation from the sun hits the Earth, and the Earth, and when energy hits something, it very rarely does it bounce completely back. I mean, after all, the Earth is not a mirror. So what happens is it retains some of that energy, and then it re-radiates or kicks back out a different kind of energy. For example, if you're wearing a black T-shirt, all right, well, you hit it with white light, it absorbs that white light, and it kicks back out a different kind of energy, usually infrared, and that's exactly what the Earth does. Mostly infrared. The problem here is that it's easy for the shortwave radiation to get through our atmosphere. It's not as easy for it to come back out of the atmosphere, and that's what traps the heat. Okay, so shortwave radiation comes in from the sun, things like microwaves and, I'm sorry, well, that's actually longer wave. Well, visible light, obviously. Visible light comes in through the atmosphere, and you can see with your very eyes that our atmosphere is transparent to visible light. But the problem is, when that bounces off the Earth retains some of that energy and kicks it back out in a different form. That is infrared, or mostly infrared, or we just call it IR. All right, that infrared is more difficult to get back out of the atmosphere. So what's going back out is different from what came in, and so that energy gets trapped in the atmosphere. Greenhouse gases like carbon dioxide and methane and chlorofluorocarbons, those are the things that are in spray cans, that kind of thing. These are gases that make it difficult for that longer wave infrared radiation, so there's a longer wave right there, that longer wave infrared radiation to get back out. Visible light is shorter wave, it can get through the atmosphere easily. These gases make it hard for infrared to get back out, and so that energy is trapped in the atmosphere. So if all the energy, if all that radiation escaped into space, the lower atmosphere would be a lot colder, so the greenhouse effect is kind of a good thing. But the greenhouse effect run amok is a bad thing because we can have too much energy causing temperatures to be driven up all over the world. This little graphic right here kind of shows that happening. All right, you can read it, I'm not going to read it to you, but the idea is that what comes in, shorter wave, is different from what the Earth bounces back out. And so you can see over here what's trying to get back out is having a lot more difficult time getting back out than coming in. So so that energy is retained. All right, like I said a minute ago, the greenhouse effect is definitely necessary. In fact, we would all be frozen here on Earth if there was no greenhouse effect. Thank goodness that CO2 and methane do hold in heat. But if they hold in too much, that poses a problem as well. Naturally, water vapor does a good part of holding in this this heat as well. You ever walk into an actual real greenhouse? It's very humid in there, and so that water vapor is doing its part in holding in heat and keeping the plants and all that stuff nice and warm and keeping them at a temperature where they can grow. But unfortunately, our human activities have really increased these greenhouse gases to the point where too much heat is being held in, and we have some other adverse effects as a result of that. We call that that should be an H in there, A-N-T-H. It's an H. Anthropogenic. A-N-T-H-R-O-P-O-G. It looks like an N, doesn't it? Anthropogenic, like anthropology. Okay, well, anthro means man or mankind or humans. All right, so this is caused by humans, and so that's a bad thing because we're overdoing it with greenhouse gases. So, of course, carbon dioxide is a really, really big one. This unit right here, ppm, that means parts per million. That means if you've got 1 million parts of the atmosphere, like atmospheric gases, like oxygen and nitrogen and all the other gases. So let's say you have 1 million atoms, let's say, of the atmosphere. That means that 200 parts of those million would be carbon dioxide, or 300 parts, or so on and so forth. It doesn't seem like very much, but it doesn't take much carbon dioxide to cause a lot of warming of the atmosphere due to the greenhouse effect. So due to things like the paleoproxy record that is looking at tree rings and looking at ice core samples and stuff, we estimated that in the past, the concentrations of carbon dioxide have been between 200 and 300 parts per million. Now we're in the range of 400 parts per million, and we think that by 2050 we could be on our way to 500 parts per million. So we're talking about a doubling or even more of the amount of carbon dioxide in our atmosphere from the way it was in previous ages. I'll let you look over this on your own, but the general idea right here is that all these greenhouse gases, carbon dioxide, this is methane, this is nitrous oxide, this is ozone, these are chlorofluorocarbons, the things that are spraying spray cans. All these are on the increase in percentages per year. So we're creating a lot of these gases and putting them into the atmosphere. Look, carbon dioxide has a really big contribution to it. Carbon dioxide and methane. These other ones, not so much. But they're all on the rise, which means it's only going to be greater and greater temperatures as we move forward. All right, so how has temperature changed over the past years? Well, these numbers are a result of looking at the paleoproxy record, looking at tree rings and looking at core samples and stuff like that. Look at this. This is kind of interesting. So times where we figured out that it was low temperatures worldwide, they coincide with glaciations. That is, more glaciers. Why would more glaciers result in lower temperatures? Actually, we know why glaciers result from low temperatures, because the lower the temperatures, the more glaciers we have, because glaciers are frozen water. But why would glaciers themselves result in low temperatures? Well, frozen water, ice, even though technically it should be clear, is generally white in color, and that reflects a lot of radiation. So the more glaciers, the more reflected radiation there is back out to space. So Earth is going to stay colder. More recently, 150,000 years ago, we have a higher sea level. All right, what does that mean? That means a lot of those glaciers had melted, and so the water was now in the ocean, which also accounts for the fact that there are less glaciers because if it's warmer, then that means that that ice would have melted and causing less glaciers. Incidentally, less glaciers means that there's less white stuff on the Earth, so less radiation reflected, and so the darker areas on the Earth under the glaciers, like the rock and the land and the dirt, are darker and are going to absorb more energy. So you have a correlation between interglacial periods, that is, less glaciers, and higher temperatures, and glacial periods being coincided with low temperatures. All right, we think about 10,000 years ago, or a little over that, there is a colder interval called the Younger Dryas. I'm not going to talk too much about the various different ages in our Earth's history. We did talk about the Pleistocene age. I'm sorry, the Pleistocene epoch. The Younger Dryas is the name of one, and the Holocene is another right here. But these are all kind of various different anomalies, being warm, being cold. There was also a little ice age as well in kind of the Middle Ages, well, actually a little bit after the Middle Ages, between the 15th and 19th centuries, the Little Ice Age, where it was considerably colder around the world. And we think that could have been because of volcanic activity. So this shows last 800,000 years, general change in temperature, up, down, up, down, up, down. Last 150,000 years, so up, down as well. Here, the last 18,000 years, it's like up, down, and then a lot of up right here. So in recent years, it seems to have been more increase in temperature, and certainly in the last couple hundred years because of us putting carbon dioxide and other greenhouse gases into the air. In the last 1,000 years, we think that it was considerably warmer, which allowed the Vikings to discover Iceland. Iceland normally would probably have been covered with glaciers and ice caps, but the fact that it was melted by that point let them discover that. Also Greenland as well, and even North America. Much of North America, if you recall back several slides ago, North America would have been partially covered by ice caps if it were a glacial period. All right. In the last 140 years, what's happened? Well, in the middle of the 1800s, we had the Industrial Revolution. A lot of machines, a lot of things sucking fossil fuels and burning them off. And so we've got a major warming trend taking place in the last 140 years. Sea levels are rising because the atmosphere is warming up, causing glaciers to melt. And we've got what you might call an interglacial period. That is why we don't have as many glaciers as we normally would have. These two graphs are even more recent, the last 1,000 years, like I mentioned a minute ago, in the last 140 years. A definite upward trend in the change in temperature. All right, Earth is definitely getting warmer as we get more recent. All right, this table right here, which I'm not going to read to you, is evidence provided by NOAA, which is the United States Meteorological Agency, and the WMO, that is Europe's meteorological agency. These are evidence for that supports our belief that the atmosphere is actually heating up and that global warming is taking place. Okay, so even without humans, however, climate still does change, even if we weren't pumping all kinds of greenhouse gases into the air. So naturally speaking, why would climate change? Well, there are things called Milankovitch cycles. And these are, you might say, natural waxing and waning of the amount of energy that the Earth retains due to Earth's orbit. The Earth's orbit actually does kind of wobble around a little bit, and so you have the Earth tilting more towards the sun or less towards the sun, causing there to be more or less energy absorbed from the sun. All right, but this happens on a small scale and on a slow scale. The large scale changes that we observe, we should probably really only attribute to human activity, not these Milankovitch cycles right here. Instead, you can say that humans are imposing climate forcing on the Earth. That is a kind of a non-natural input that causes Earth's energy to either increase or decrease. We call it a positive feedback or a negative feedback if it decreases. For example, a positive feedback would be, let's say, Earth's glaciers melt. Okay? Earth's glaciers melt, and that means there's less ice, and so there's less reflective stuff. There's more dark area on the Earth, which causes the Earth to absorb more energy and make the temperature colder. I'm sorry, not temperature, make the temperature warmer. All right, the warmer the temperature, the more glaciers melt, which means the more dark area you have. So we call that a positive feedback. It keeps perpetuating itself. A negative feedback is something that you have something happen, but what that does is that undoes the original thing that caused it to happen. A good example, you might say a negative feedback is, let's say you have a cup of water over a fire. All right, well, that fire, it won't burn through the cup if there's water in it. Let's pretend that it did. Let's just pretend that the fire burned through the cup. All right, well, that means the water would come through and then burn down and put out the fire. So negative feedback means that what happens eventually undoes the thing that caused that to happen. So things return to kind of like an equilibrium. Climate sensitivity, that's a good term. It describes how does the climate respond when we have a new equilibrium. All right, and of course the response time is how long does it take for the climate to actually respond. All right, this can be on the order of a few years or on the order of thousands of years. Depends on how sensitive the climate is. All right, all these things are different variables that cause climate forcing to take place. Ice sheets and vegetation. Remember I said that the more ice sheets, you might have more energy reflected away from the Earth. The more vegetation you have exposed, it might be more absorbed by the Earth because vegetation is darker. Greenhouse gases play a big part in holding in heat. All right, that's one of the things that forces climate. Also aerosols as well. That is the particles that are in the air, smoke and water you might say liquid droplets and that kind of thing. All these are various different varieties of climate forcing. Okay, once again, I'm not going to read through all of this to you, but you might think that aerosols in the atmosphere are bad. Well, actually not necessarily, because look, all these things produced in the industrial age since the 1700s, CO2 and nitrous oxide and ozone and methane and stuff, these cause temperatures to go up. All right, but one of the things, you might say a negative feedback from the Industrial Revolution, starting in the 18th century, is the aerosols. Remember aerosols, like smoke particles, what they do is they block or they reflect back energy from the sun. So look, they're having a negative impact on the temperature in the atmosphere, which is kind of good, and to some degree these balance out these gases that retain more energy than we should have. So those are good examples of positive and also negative forcings with regard to temperature of the atmosphere. But if you really just look at the greenhouse gases, the positive forcings, that is the greenhouse gases causing more energy to be trapped. Between, in the last 200-300 years, these greenhouse gases have just rocketed up exponentially. All right, all this information, were we around to take this? No, we weren't. But all this information about the greenhouse gas concentration was wrapped up in things like tree rings and core samples and that kind of thing. Well, in the past couple hundred years, we've been able to actually measure these ourselves, and the measured values of these greenhouse gases have really just shot through the roof. All right, so what are some other things that we can look at to see if climate is changing? Well, there's a thing we call the ocean conveyor belt. It's not really a belt. I mean, ocean is just water. But what we mean by that is we think of the oceans as being kind of like these loops of, you might say, currents of water that swish back and forth from one end of the oceans to the other. It's one big circulation loop through all the oceans. All right, and depending on how this water, the temperature of the water in these parts of the oceans changes, that can cause fast changes in climate. We have a very warm conveyor belt near us. We call it the Gulf Stream, all right, off our east coast, which is what causes our east coast waters to be fairly warm. All right, well, as it moves towards the North Pole, water cools and then sinks down, and then it moves along the bottom right there. So you can think of it as a big loop or a big ribbon of water that moves around the oceans. Europe, like for example, Europe, right? You have this this part of the conveyor belt moving up past Europe. So the warm water comes up past us, hits the Gulf. Well, we call it the Gulf Stream because it comes from the Gulf. Comes up our east coast, swishes across to Europe right here, still warm, and then it cools and sinks back down, and now it's blue. All right, so our east coast and Europe benefit from warmer waters. Well, if you can really call it benefiting. But Europe is definitely a lot warmer than it normally would be because of that warm water off the coast. And so, I know I mentioned this before, but ultimately we think this is happening because of human interactions. All right, us kicking out all kinds of greenhouse gases because of burning fossil fuels into the air. Whenever we emit any kind of gases that trap heat, it causes this temperature to go up. And so we're finding that not just in the atmospheric temperature, but also in the sea surface temperature as well. One thing that we can discover from tree rings and core samples and ice samples is the energy output from the sun. We call that solar forcing. All right, the sun actually does vary. All right, it's the sun right here. Sun does vary in its output, and we can measure that by looking at tree rings. All right, so possibly the sun is responsible for a warm period in the Middle Ages and the Little Ice Age towards the end of that right there. More output or less output from the sun. So this is part of the explanation for climate change, but certainly not all of it. Another thing that can have a forcing effect is volcanoes. Remember I said a minute ago how particles in the air, aerosols like smoke and that kind of thing, we think of as being pollution, and pollution is bad. Well, volcanoes kick out their own kinds of aerosols as well, their own kind of natural pollution. Well, the good thing they do is actually can have a cooling effect because they block out sunlight or reflect sunlight back into space. Mount Pinatubo in the Philippines in 1991 really kind of knocked back global warming for the next year or so because of all the particles it put into the air. This is, I'm not sure if this is Mount Pinatubo or not, but all these aerosols, man, that's a lot of ash right there. That's a lot of blocking of the sun's energy that Mount Pinatubo did. And so that's kind of a forcing effect that is done naturally, not just by different solar output, but by actually volcanoes erupting and blocking some of that solar energy. But of course, there's human-based forcing, or anthropogenic forcing. Remember, anthro meaning man or mankind. All right, so when we emit greenhouse gases, that plays a really, really big part in trapping in heat. So we seem to have the trump card in terms of what direction we're going to make the atmosphere go. We can choose to or not to burn fuels that emit greenhouse gases, but because we are doing that, we have a considerable amount of warming per decade. All right, 0.2 degrees Celsius per decade. It doesn't seem like very much, but over the course of 10 years, or over several decades, over the whole Earth, that temperature rising up, that's a significant amount. It's a lot of energy over the whole Earth. Since the Industrial Revolution, the Industrial Age, burning fossil fuels, burning oil and gasoline, that kind of thing, puts a lot more carbon dioxide in the air than it would normally be. And so, models that we create based on the way we burn fossil fuels basically say that, that the sea level is going to continue to rise, and it's really a result of human activity above anything else. Above solar forcing, above volcanic forcing, it's really anthropogenic forcing that is causing this rise in global temperatures.